It's a pleasure today to welcome Zhongxu Zhai to give us a seminar. Zhongxu is a postdoc at the WCA. He's been with us now for 5 months or so. Unfortunately, or at least maybe unfortunately is the wrong word, but he is actually going to be leaving in September. He has been offered a faculty job in Shanghai. Congratulations. We'll be sad to see you leave. What we try to do is get our postdocs to give a seminar to introduce their work and introduce themselves to everybody else. This is particularly important now for Zhongxu, so if you want to work with him, get his perspective on things, you have to do so quickly, at least before September. So Zhongxu got his PhD from New York University in 2018. He did one postdoc at Caltech for 3 years before coming here last year. Looking over his CV, the most impressive thing for me was the number of first author papers he has. I think the count was 19, which is what every month. So anyway, he's going to tell us today about large-scale structure from galaxy redshift surveys. Thank you.
Happy to have this opportunity to introduce my work in the past few years. So today I will talk about the logical structures and their applications for the cosmology. So this is this is outline of my talk. So I will start with the brief introduction of the background, and then I will focus on the logical structure analysis. In particular, I will focus on the future redshift surveys and the information at nonlinear scale. And the last part is my summary and future plans. So let's start with the concordance cosmology. This is one of the most important establishments in the past few decades. Based on many experiments and observations, we have very good knowledge of the basics of modern cosmology. So the observational data includes, for example, the Planck cosmic microwave background. And we have the early measurements from WMAP, but updated results from the Planck mission. So measure the temperature fluctuations, and we have the CMB lensing and polarization. So we have accurate measurement of the fundamental parameters. So in addition to these CMB measurements, we have the galaxy datasets. So we can measure their spatial distributions and use the clustering signals to measure their expansion history of the universe and the growth history of structure. So the two main probes are the BAO and RSD, and that I will introduce a little later. So in addition to these experiments, the last one and perhaps the earliest one is the type 1 supernovae. We can use the luminosity distance and redshift relation to measure the expansion history of the universe. So combine all these different probes together, we finally arrive at this concordance cosmology, or the standard lambda CDM model. So this model is simple. It has only a few parameters. But in this model, the dominant part of energy matter components is dark. So dark matter or dark energy. And the ordinary matter is only like 5%. So these components gives us one of the biggest questions in modern cosmology. So what causes is cosmic acceleration. So the theoretical physicists have proposed many different candidates, and these candidates can be classified into two main categories. One is the dark energy, and the other one is modified gravity. So for dark energy, it introduces a new energy component with negative pressure. So the simplest one is the cosmological constant. The other theories like scalar field, or the other like Chaplinian gas or holographic dark energy. For modified gravity theories, so this model doesn't need a new energy component, but it can change the general relativity at cosmic scales. So among these theoretical research and observational research, it's important to combine the datasets to constrain their parameter space and better understand the nature of dark energy. So here I will focus on the usage of the information from particle structure. The main probes are the BAO and RSD. So for BAO, it is from the early universe that the temperature is very high, all the matter and the photons are coupled together. So any perturbation can grow and propagate into some distance until the photon decouples. So it gives us the final results that matter distribution is more clustered at a particular scale. This is the baryon acoustic oscillation scale as 110 meg per second. And this scale only depends on the physics of early universe. Since the galaxies are biased tracers of the dark matter density field, we can observe the spatial distribution of the galaxies, and we will see similar patterns or features in their spatial distribution. And when we observe this BO feature, we can use them as a standard ruler to measure the distance at different redshifts. So it gives us measurement of the expansion history of the universe. So the second probe is the redshift space distortion. It is from the fact that for all the objects we observe in the sky, their spatial positions is determined by their redshift, because their redshift has two components. One is the Hubble flow, or the expansion of the universe. The second one is the peculiar velocity. So at the linear scale, this peculiar velocity can increase their clustering amplitudes along the left side. So when we observe these 2D measurements for correlation function of power spectrum, the result is kind of squashed along the left side. At the very nonlinear scales, so since this peculiar velocity is much higher, can be higher than the Hubble flow or the expansion of the universe. So the net effect is like random motion. So the measured power spectrum correlation function can be squeezed along the left side direction. But we can use this information constrain the linear growth rate of structure and constrain cosmical parameters. So these are the two main probes from the galaxy space distribution. With the measurements from different surveys, and one of the most important one perhaps is from SDSS, we have measurements across wide redshift range, and we can project their constraints in terms of a few parameters like omega matter or sigma-8. So here I show one of the latest results from the EBOS team in 2020. So as you can see that here, the figure compares individual experiments like DES, mostly for galaxy lensing, and the Planck and SDSS. So apparently these different experiments have different degeneracy directions. And then there are some uncertainties for these parameters. Important thing of these different probes is that they are sensitive to different parameters. This figure is even clearer for this kind of feature. So for SDSS, large structure measurements is sensitive to the space curvature. As you can see, the blue contour or the 1D distribution is much tighter than the other ones. But on the other hand, the supernovae measurements is more sensitive to the equation of state for dark energy. From these figures, although the lambda CDM model is still favored or preferred by these experiments, but we can notice that even for this one of the simplest model for dark energy, there is only 2 or 3 parameters in addition to the lambda CDM model. The uncertainty is still large. We combine all these experiments, the constraint on W is like 10 or 20%. So it means a large family of dark energy or modified gravity models are still allowed by these observational data. So how can we better understand the nature of dark energy and better constrain their parameters? So then I will focus on the logical structure and their applications for this. So the first one is to design and use the future galaxy redshift surveys. So here I list a few programs in the future. For example, the first one is the Euclid, which is scheduled to be launched next year, and the Roman in 2027, and its successor Atlas. Although Atlas is just for now is a mission of a concept at this stage. So here, all these missions will have different specifics. For example, they can have different scale area and different tracers for galaxies, but they can provide complementary information to each other. So here I will focus on the Roman and use the results as example. So Roman will observe different objects, and it has multiple aspects for astronomy. So for cosmology, it has 3 main probes: the galaxy redshift survey, the weak lensing, and the supernovae. So here I will focus on the galaxy redshift survey using the emission on galaxies. So Roman is a unique probe to measure the cosmic structure formation history over a very wide redshift range. The tracers will include emission on galaxies, and galaxy clusters and lemma brick galaxies. So for the large structure analysis, the main galaxies will come from emission line galaxies from 1 to 3. So it is important for us to understand, for example, the number densities of these galaxies and their clustering signals. Perhaps one of the most important questions is that can we use these galaxies to better measure the large structure analysis signals and constraint cosmology? So this emission line galaxy survey will be based on this high latitude spectroscopic survey. So this is one of the Roman programs. It is a 2-year program and optimized for dark energy studies. The sky coverage is 2,000 square degree. So we need to understand the number densities and the types of emission lines of these galaxies. So the reason is that we need to better understand the survey and optimize the survey strategy. So this can assure that we can reduce the uncertainty in the cluster measurements as their final constraint on the cosmological parameters. So for such work, our idea is to generate a catalog of galaxies. And in practice, there are multiple ways to do that. For example, we can do halo occupation distribution. So it is an empirical model. It can statistically describe how dark matter halos are populated with certain types of galaxies. So this method is simple and straightforward. It has been used for the large structure analysis for years and has very wide applications. But these methods need the observational data at the relevant redshift to calibrate their parameters. So for future surveys like Roman or Euclid, this is not available. So the second method is the hydrodynamic simulation. It can simultaneously evolve the dark matter particles and gas particles from very high redshift until low redshift. So it considers gravity and the other baryonic processes. So this model can output very detailed galaxy properties, like their brightness, the star formation history, and so on. But this hydro simulation is expensive. So the typical volume of hydro simulation is only a few hundred meg per second. So for large-scale analysis, for the purpose of cosmology, this volume can be limited and not quite useful. So the third method is the semi-analytical model, or SEM. So this method can parameterize many astrophysical processes as differential equations and solve these equations in the background of dark matter halos and emerger trees. So it is, compared with hydro simulation, it is larger and it is faster. And compared with halo occupation distribution, it can make more predictions for galaxies. But it also requires calibration, but compared with HOD, it's easier. So this is the method we choose in our simulation. So in particular, we use this Galacticus model. It is written and maintained by Andrew Benson and Carnegie. So this figure describes overall pipeline for Galacticus. It is also similar to the other SEM, like Gulf form or L galaxies. So this model starts with a cosmological model or parameter site. And then we run simulations for dark matter halos and emerger trees. And then we put these astrophysical processes in this background and evolve all these differential equations. And these processes include the gas cooling, star formation, and feedback from supernovae and black hole, and even dust attenuation. So since these astrophysical processes have free parameters, and then the final galaxy catalog can depend on these free parameters, we need to make sure the galaxy catalog is reasonable. So there is a calibration process. So in this process, we choose some observational data sites and compare the galaxy catalog. So after this calibration is done, we can just enter the final production mode. So in our calibration, we can choose a stellar mass function or luminosity function from the current data. For the Roman simulations, we choose since the main tracers of the emission galaxy of Roman is HR and O3 emission lines. And there are some available data from surveys like HISOS and WISP. So we choose this HR luminosity function and number density to calibrate our model. So after calibration, we can produce the final galaxy simulation and estimate and answer the questions related for the forecast. So for galactics, the inputs or the ingredients is the talk about the halo catalog and the merger trees. It is from the unit simulation. So the unit simulation has multiple boxes run by different codes. So there are 4 boxes or 2 pairs of boxes run by gadgets. It has these boxes. The box size is 1 gig per second boxes, and the particle mass resolution is like 10 to 9 solar masses. So in addition to these gadget boxes, the unit simulation also has a few hundred approximate mocks run by FastPM. They have different box size and mass resolution, mainly for convergence test. So this unit simulation applies this inverse phase technique. So here I show this movie for this unit simulation. It's from a 1 pair, the 2 boxes. So these 2 boxes have the same cosmological parameters, as the amplitude of the initial conditions are the same, but inverse phase. So this technique can suppress the sample variance of the halo statistics and also the galaxy statistics. So with this technique, the effective volume, although it is only 2 boxes, but the effective volume can be much larger than 2 boxes. So from this simulation, we identify the halos by the Rockstar halo finder and build the merger trees by the consistent trees. So here I show one example of these merger trees. The 3 panels are just the 3 Cartesian coordinates. The y-axis is the redshift. So as you can see that at very early redshift, there are many small halos. They can move and merge to form bigger and bigger halos. The size of the dots are roughly proportional to their halo mass. So this is another example. This is one of the biggest trees in the unit simulation. So our model involves all these more than 100 million merger trees and produce the final galaxy catalog. So this is the light cone for the cosmology simulation. It has a coverage of 2,000 square degree. And for reference, this figure shows the emission on galaxies from other ground-based surveys, like EBOS and DESI as the orange and the blue lines. The Raman galaxies will be attracted 1 to 3, and you can see many structures here. So from these simulations, in addition to these cosmological simulations, we have another version of smaller survey area for the galaxy simulation, mainly for the galaxy science. So this catalog has a redshift range of 0 to 10, much wider than Raman or Euclid. We also output the spectral energy distribution for these galaxies in the wavelength range of 0.2 to 4 microns. And this catalog also includes emission luminosities like H alpha, H03, and O2 and N2. But given the current accuracy of the model, our prediction for H alpha and O3 are reasonable. The predictions for the other lines need improvement in the future. The galaxy catalog also includes the broadband magnitudes for Raman and Euclid. So it can be used for the other forecast analysis. So the figure here shows the effect of the flux limit. So here from left to right, it is for the Raman deep, Raman nominal, and Euclid flux limits. They are 0.5 or 1 or 2 times 10 to the minus 16 erg per second per centimeter squared. As you can see that as we reduce the flux limit, more and more galaxies can be observed. So it will be good to have a better number of galaxies and increase the clustering to reduce the uncertainty in the clustering measurements. So from these galaxy simulations, the small simulation or cosmological simulation, we can make a few predictions. So here I show one example, which is the photometric completeness. So it is defined as that for a given H-band magnitude cut, what is the fraction of galaxies above some flux limits that can be observed? For instance, if we look at H alpha galaxies, if the H-band magnitude cut is 24, for Euclid, the completeness will be 97%. Since Raman has a better flux limit, the completeness will be slightly lower. It's like 95%. For O3 is similar, but relatively lower. So this result is only from this simulation itself. There are some other methods. For example, we can use the available catalog from WISP and apply the survey strategies that can mimic Euclid or Roman and make the similar prediction for this photometric completeness. And we compare these results and the observation-based results, and they are quite consistent. So from these galaxy simulations, the one project we are working on is the algorithm simulation. So it is to estimate the quality of the data to better understand the completeness and purity for the large-scale structure measurements. So I will show a few preliminary results. So here is one of the direct images from the one of the Roman bands. They are from this galactic simulation. So from this galaxy catalog, we made another simulation based on axisym. It is the 2D spectrum of this field of view. You can see many objects and their spectrum. So this is only preliminary results. The next thing we will consider is some observational systematics, like the roll angles or dithering and the other detectors. So finally, it will give us estimates of the purity of this galaxy catalog. So this is for the galaxy size. For cosmology, the usage of logical structure, we measure their number densities of different tracers and their linear bias compared with the dark matter. So with these results, we can predict the cosmological constraints based on methods like visual matrix. So this figure is our forecast for the cosmic distance scales and the linear growth rate. So the top panel shows the angular and the radial distance, and the bottom panel shows F sigma 8. So the current data from SDSS are shown as the solid symbols, and our predictions based on Roman is open symbols. As you can see that it is clearly shown in the F sigma 8 that the emission galaxies will cover redshift range from 1 to 3, and the uncertainty of this measurement is comparable to the Bose galaxies. But the Bose galaxies has much larger survey area. It's like 10,000 square degrees, but the Roman is only 2,000 square degrees. So with this data set, we can expect that the constraints on the cosmological parameters will be improved significantly. So with these Roman simulations for either galaxies or cosmology, we have done different tests and analysis. For example, their halo occupation distribution of these emission galaxies. We can use this information to understand the connections between these emission galaxies and diagonal halos. This HOD and the linear bias are already done, and the algorithm simulations and their forecast for the purity is some ongoing work. And in the near future, we plan to investigate the, for example, O3 galaxies. Our current prediction is mainly based on the H alpha. With O3 galaxies in the future, we will have another boost in the constraining power, and also the combination with other programs. That will be the future works. So for our forecast for Roman and the other actual analysis, the current analysis based on Bose and eBose data sets, the large structure measurements is based on the linear scale, where we have a good understanding of the perturbation theory. So we can extract the cosmological information from the cluster measurements. But at this linear scale or large scale, the measurement itself is affected by the sample variance. So on the other hand, at smaller scales, our measurement is much more accurate. So perhaps we can use these small scale measurements to constrain cosmology. So this is an important question, but also challenging, because at small scales, we don't have a simple theory to describe the nonlinearity of the dark matter dynamics. In addition, at these small scales, we need to consider the baryonic physics or the galaxy bias. So it makes these results difficult, makes this analysis difficult. So in order to investigate such a problem, this also the third part of my talk at the information nonlinear scales. We proposed and developed this emulator method. So this is based on this Emulus project. So In this project, we produce multiple dark matter simulations with different cosmologies. So with these dark matter simulations, we can use them to model the nonlinear dynamics of dark matter. And from these results, we can combine these results with the product for dark matter, halos, and galaxies with some machine learning methods to model the dependence of statistics on cosmology and galaxy bias. So from this Emulus project, we have built the emulators for halo statistics and galaxy statistics. The final product of this emulator work is to make fast and accurate predictions for the statistics, like the halo mass function, halo bias function, or galaxy correlation function. So with these results, we can now simultaneously model the nonlinear dynamics and the galaxy bias, and use this information to constrain cosmology. So here I will focus on the application of this galaxy correlation function. So this flowchart describes the procedure of this emulator approach. So we first design a Latin hypercube in the cosmological parameter space. And for each point in this Latin hypercube, we run n-body simulation. And from the product, we compute the quantities of interest. It can be matter or halos or galaxies. So from this simulation to galaxies, we need another model to connect the halos and galaxies. So it can be a halo occupation distribution or abundance matching model. So the quantities of interest are usually the summary statistics, like the 2-point correlation function or power spectrum. So with these results, we can combine them with the interpolation scheme. So here it can be Gaussian process or neural network. So we have tested, we have done some comparison of these different methods. It looks like for the data sets of this work, the Gaussian process can make more accurate predictions than neural network. So after this emulator is ready, we can make predictions at the new points in the parameter space, and the results has accuracy that is comparable or even better than the simulation directly. So with this emulator for galaxy correlation function or power spectrum, we can run MCMC to constrain the cosmological parameters. Well, this is by comparing the theoretical predictions with observational data. So here I will focus on the galaxy clustering and nonlinear scale, and you introduce their cosmological constraint. Since in this model, the parameters include cosmology and galaxy bias. So this analysis itself is a test of cosmology and general relativity. And then one of our goals is to measure the linear growth rates using the small scale measurements. And in this work, we introduced another 3 parameters, which is it's called gamma f. We use this parameter to scale the velocity field of the dark matter halos predicted by this n-body simulation plus general relativity. So we allow this parameter to be a free parameter. So when this parameter is 1, it means it is just the prediction of general relativity. If it is different than 1, it means the velocity field is different from this general GR prediction. So we used observational data to constrain these parameters. So along this direction, we first did a theoretical attempt. So here we target the same mass galaxies from BOSS at the redshift 0.55. We built emulators for the real and redshift space correlation function, including the projected correlation function with WP and the redshift space multiples. So here the 3 columns shows the 3 statistics, and top panel shows a few examples for the comparison. The circles here are the direct measurement from the simulation, and the solid lines are our emulator prediction. So as you can see that our emulator can accurately predict these galaxy statistics, although the top panel only shows a few examples. So in the bottom panel, we show the overall results of this emulator prediction. So this is obtained by a few hundred test samples. And we find that from this nonlinear to quasi-linear scale from 0.1 to 60 microparsecond, the emulator accuracy is better than sample variance. For the most informative scale of multiple in the middle from 1 to 10 microparsecond, the accuracy is like 1%. It is even better than sample variance. It means the emulator prediction is more accurate than the simulation itself. So with these emulators, we can now answer the question that is there more constraining power to constrain cosmology or linear growth rate at small scales? So we compare, so we project this constraint in terms of F sigma 8 and compare the results with the linear scale measurements. So on the right-hand side, I express the results F sigma 8 and compare the small scale measurements with the large scale measurements, which is the star here. So the solid and dashed lines shows the measurements as a function of minimum scales used in analysis. So the fiduciary result is the solid red line. As you can see that if we have a minimum scale of 0.1 microparsecond, the measurement of F sigma 8 is like 5%. And the large scale measurement is like 10%. So it means, so compare these two results. It tells us that the small scale measurements can improve the constraint by a factor of 2. So this result is promising. And we can apply these emulators to the current data sets from SDSS. So one application is these eBOS luminous red galaxies. So from Max results. So this figure shows the comparison of the linear and the nonlinear results. The figures on the left and right are almost the same, except for the blue and the green contours. So the orange and the red are from the other surveys like DES and the Planck. And the blue and the green contours are the constraint from this cluster analysis. The difference is that on the left-hand side, we consider the full scale from nonlinear to linear scale. On the right-hand side is linear scale only. So as you can see that it is consistent with our previous page that the nonlinear scale can shrink the contour significantly. So if we compare the green and blue in the left and right. But on the other hand, we can notice that there seems to be some tension between the small scale cluster measurements and the other experiments. And I will talk about it later. So in addition to these eBOS galaxies, we also apply this emulator to the BOS galaxies. Since the BOS galaxies have a wide redshift range from 0.2 to 0.6. So we split the galaxies into 3 redshift beams, and we built emulators for individual redshift beams. So this figure is the measurements of the collision function and our best fit model using the emulator method. So here I just remind that in this emulator work, the parameters including the include the cosmological parameters and galaxy bias parameters. For the galaxy bias parameters, we include the basic HOD parameter to describe the clustering dependence on halo mass. And in addition to these fundamental HOD parameters, we also consider the galaxy kinematics, which are modeled by the velocity bias for central and satellites. And we also consider the concentration of the satellites relative to the NFW profile for dark matter. And the last thing is the assembly bias. It is bias caused by the clustering dependence on parameters other than halo mass. So in this model, we consider the local environment or the local density of the dark matter halos. So the constraint comes from the real space and redshift clusterings. And you can see that our best fit model can perfectly match the observed measurements. And from these measurements, we express the final measurements of F sigma 8 in this figure and compare our measurements with the other analysis literature. So here we split the analysis into linear scale as the open symbols, and the solid symbols are the nonlinear scale measurements, including our work and Max eBOS results and other similar analysis. So our result is the black and blue squares. As you can see that it looks like all these results are lower than the Planck prediction, which is the horizontal shaded area. The tension is highest for the high redshift at 0.55. It's like 4.5 sigma. At two lower redshift beams, the tension is slightly better, but also lower than F sigma 8. So in addition to these measurements, we can see that the small scale measurements has much smaller error bar compared with the large scale measurements. So given these results, how can we understand it? So there are a few possible explanations. One is that perhaps general relativity needs some modification at cosmic scales. Since we have this additional parameter to scale the velocity field, we projected a constraint at the 3 redshifts. It looks like there is some scatter, although one of the beams is slightly different from the general relativity. But these 3 redshift beams have different measurements. But we noticed that for these clustering measurements, most of the information is for the velocity field. So this parameter is degenerates with the other cosmological parameters, especially F sigma 8. So if we consider this degeneracy, it looks like all three redshifts have very consistent results. But if we compare these combined parameters with the Planck measurements, it shows that our result is lower than Planck. So the second possibility is that perhaps the Planck parameter is slightly biased. So this figure is the 2D contour plot for gamma F and sigma 8. So it is clear that our clustering measurements is lower than Planck prediction. So we noticed that in this kind of result is also discovered by the other galaxy analysis. For example, the lensing is low effect. So when people use similar galaxies, the CMS-LOSY galaxies, and measure the galaxy lensing signal, which measures the axis surface density around galaxies, and compare this result with the Planck prediction, the amplitude of this lensing signal is also lower than Planck results. So the figure on the bottom is this. In this figure, the solid and different lines are from this Planck cosmology, but using different simulations with some different details. But all these simulations seem to have a higher amplitude than the lensing magnitude measured from the Bose galaxies, and the difference is like 40%. When we project these constraints in a cosmological parameter space, we can find a similar constraint at our clustering axis. So the third possibility is that maybe we need more degrees of freedom. For our current analysis, we assume that the neutrinos are massless. But from the particle physics experiments, we know that at least one of neutrinos are massive. And these massive neutrinos can surprise the growth rate of structure at small scales. So this figure is from one of the simulations, and the neutrino mass is much higher than the current experiments. It's just to highlight the effect caused by these massive neutrinos. So with this effect from massive neutrinos, we plan to add these massive neutrinos in the next generation of immular simulations. And when this simulation is done, we will redo the analysis and compare the constraints to make sure if this discrepancy was caused by these neutrinos or not. So the last possibility is that perhaps there is some observational systematics. So in our analysis, we applied some selection of the galaxies to define a volume limited sample. But this selection depends on the luminosity or number densities. So in order to test this possibility, we construct galaxy samples with different thresholds of luminosity and build different emulators and reanalyze the clustering measurements. So this figure shows the contour plots in the cosmological parameter space. It looks like all these the galaxy samples with different luminosities also give very consistent constraints in cosmology. So in addition to this luminosity, the Bose galaxies also have the value-added catalog. So from this catalog, we have access to parameters rather than this luminosity. We have the measurements of, for example, the color, the age, and the stellar mass, and the star formation rate. So it means we can split the galaxies by these properties. And we know that the galaxies clustering can depend on these properties. For example, the red galaxies are more clustered than blue galaxies, and old galaxies are more clustered than young galaxies. So if we split the galaxies by these properties, and we reanalyze by this emulator method and projects their constraints by F sigma 8, then this is the result. It looks like no matter how we split the galaxies, all their constraint of F sigma 8 is consistent. It's always lower than the Planck prediction. So here I show the results split by luminosity, age, color, stellar mass, and last one is specific star formation rate. So this is the possibilities from the observational side. There are some other possibilities from the theoretical part. For example, perhaps our HOD model or the halo model is not ideal for this cluster analysis, especially we need to consider more baryonic results at small scales. And this will be our future work in the next couple of months and years. Okay, so this is the summary of my talk. I have introduced our forecast for Roman and Euclid, his future surveys, and also introduced the emulator work for the nonlinear scale cluster measurements. I will stop here and take questions. Thank you.
Excellent. Thank you, Zhongxu. James, you raised your hand very quickly.
Yes, that was a combination of clapping and hand raising, but the hand raising won out. So just on that last point about the growth rate being too low, is there any kind of, could an assembly of, you said the HOD might be the source of the problem. So if you had some sort of assembly bias-like effect,
yes,
is there a sort of obvious way to figure out what direction that effect would have to go in to explain these results? I mean, suppose cosmology is Planck and it's something about the HODs that's not giving the right result. Is there an obvious way to shift the HOD model by selecting more or less clustered galaxies?
Well, in our current model, the assembly bias is modeled by the local density. Mm-hmm. So it can shift the HOD parameter slightly. This model has already been implemented in our analysis. The other test is that we can split analysis at different scales. For example, we can test analysis at linear scale or nonlinear scales. So for example, in Mac's paper for EBOS analysis, we consider the full scale or nonlinear scale, which means the information is from the two halo term or one halo term. It looks like there is some slight discrepancy between this one halo term and two halo terms. So this is just my guess. So perhaps the possibilities in this one halo term modeling. For example, our current emulator assumes that the satellites are followed by this an FW profile, although with the extension for concentration. But their spatial distribution is like spherical distributed. So, but for one halo term, sometimes we need to consider the halo shape. It can change the one halo term distribution. So this is one of the tests that I plan to do in the next.
Okay, thank you.
Thank you.
And just a comment on that, I think it's very interesting that we're now seeing sort of internal inconsistencies in these results at this level. And this is, I think, this is telling us a lot. Mike?
Yeah, I'm glad that RSD people are finally coming around to low sigma 8. That's always a good thing to see.
I would not go that far.
Very conservative. I noticed you guys always...
Mike, these internal inconsistencies
that
we've seen show that we get low and high values. On
Mhm.
average, it's the low because the small scales win out often.
Yeah.
But I would not use such strong language about
All
coming
right.
around to.
All right, fair enough. You should show the kids' results if you're going to show lensing as well. It's usually hangs a little bit lower than the DES ones.
Oh yeah.
And I won't even mention the other peculiar velocity stuff that's not RSD based. But my question you partly preempted by said you were going to look at baryonic effects. Baryonic effects, of course, are hard to understand. They're hard to model. They're expensive to model. If you run a full hydro sim. So I'm guessing that running full hydro sims in an emulator mode is, with these Latin hypercubes is beyond the realm of feasibility.
I think so. My understanding is that hydro
And so then
simulations-
how do you marginalize over potential small scale baryonic effects and cosmology at the same time?
Yeah. Well, perhaps the current volume from a typical hydro simulation is okay for the small scale analysis because we don't need to worry too much about the sample variance at large scale. But we need multiple simulations, at least, like, for example, we use 40 cosmologies to build the emulator. I guess if we switch to hydro simulation, we need similar amount of simulations.
Yep. And that's expensive. So
Yeah.
it's a tricky problem.
Mahesh?
So thank you, and sorry I actually missed the beginning of the talk, or I guess most of the talk, but I had a couple of questions that kind of jump at me. This internal inconsistency, can you kind of elaborate a little bit? I think I missed most of it. So is there like a plot that shows this internal inconsistency?
Give me 1 second.
I mean, I think one of the plots was the redshift ranges, which you showed, right? You showed a plot where isolating in redshift gave different results.
Isolating to redshift.
But that, I mean, I guess you can say there's a model that varies significantly with redshift, but there's scale and color dependent ones as well.
Yeah, if something that's, I would say if it varies from galaxy to galaxy type, then that would be more internal inconsistency.
Let me share this the draft I prepared. So can you see these
yes
3 panels?
Yeah.
Let me make it.
This is the distance range, right? Okay.
Yeah, so we split this analysis into, for example, linear scales and nonlinear scales. For example, the blue contour is we use the full linear scale, full nonlinear scale from 0.1 to 60 meg per second.
Right.
And the red is from 0.4, and the green is 3.5, which is transition from 1 halo to 2 halo term. Basically use all this linear scale information. So the 3 panels are for 3 redshift bins. As you can see, when we go to smaller scales, switch from 2 halo to 1 halo term, there is some discrepancy.
Well, that doesn't look like a discrepancy. I mean, they are consistent.
Well, yeah, the consistency is from this large uncertainty of these linear scale measurements.
Yeah. Okay. I mean, and it's a bit hard because you're including everything in the blue curves, or the blue, I guess, histogram. So, but if you could actually split them up to a small scales and versus larger scales, different data sets, basically, then you could quantify whether they're consistent or discrepant. But yeah, I mean, I think I would be a smoking gun as to whether
that's exactly what I was thinking. They're not independent, so it's hard to say, right?
Right.
And this doesn't say that lambda CDM is right. This does say that there's some problem with the model. transmitting to the data.
Where do you see the problem? Because I mean, yes, they've shifted, but I mean they're within the error, consistent with each other. So
Yeah, I'm with Nayesh on that one.
But, well, these samples should be independent.
Yes.
But actually, they're not.
That will tell you whether they're really
No, I
inconsistent.
mean, the different redshifts are independent, right?
Oh,
So
yeah,
you've
yeah.
got two of them where
I was just looking at the scales. Isn't everything they don't look that inconsistent to me with each other. If you pile them all on top of each other is what you're saying.
Well, they have different redshifts, so their measurement of F sigma 8 is slightly different.
Yeah, I mean, this is F sigma 8 at that redshift, right? Not
Yes,
F sigma 8 extrapolated to 0. So it's hard to tell what the correct answer would be.
All of these and the EBOS ones all show a larger value of F sigma 8 the larger scales you fit.
Yes, the Max paper, yes.
Also worth pointing out in an unrelated paper that didn't use an emulator and Longi et al., they also found a pretty strong scale dependence. But as you're saying, when we did this in the EBOS picture, when you take all the scales together, they are consistent. So we didn't have an issue in putting our results forward, but internally it's concerning for us because it shouldn't be the case. We're seeing this in every sample we look at with the same kind of shift. So
you're talking about the scale shift, not the. I'm confused between the redshift dependence and the scale dependence, which are both present.
Well,
which is your?
It's the scale dependence, but it's seen in the same way at every redshift in independent samples.
I see what you mean. Okay, I see. Well, 2 are higher and 1 is the same,
And then there's another one that's higher.
Okay, not shown here.
Another analysis that's also higher, not shown. Yeah.
Not shown here. Okay. So.
Right.
But this still says there's a problem, but it's pointing more towards the problem being the way the HOD is modeling the smaller scales, or there's something fundamentally wrong with the way we're simulating the smaller scales. It just, it doesn't immediately point to the linear, very large scales being the issue.
Yeah. No, that's very fair.
For what it's worth, our stuff is, I think, mostly on large scales, certainly bigger than 3 megaparsecs, and it gives you the lower S8 as well.
Interesting. Okay, that's it. Thanks.
Okay, let me go back to my slides.
Are there more questions? I think we might be done, Zhongxu.
Okay, great.
All right. Thank you, everybody.
Thank you very much.
Thanks very much.
Enjoy the snow.
thanks, Zhongxu. Take care, everyone.
Stay
Okay, bye.
safe. Bye.